Welcome to Workbook Statistics. This time I'm going to talk about different statistical terms which will come up across different parts of the workbook. The first differentiation could be with regard to data types. Here this table in a most illustrative way shows us which are the three most important data types we might come across. Usually if you get data, it's cross-sectional data, meaning for one point in time, you collect data for different observations. For example, if you conduct a survey, you have one point in time where the survey is conducted, different participants who are the cross-sections. If, for example, you study unemployment data for 1 year, but from different set of countries, that's one point in time, different cross-sections with the countries being the different cross-sections. That's one way to think about this. A slightly bit more sophisticated perspective are time series or longitudinal data. Time series means I have one observation, one participant, and multiple points in time. So for example, I'm going to take a look how one person develops in their math skills while learning throughout the whole semester. I take a look how the unemployment rate in Germany developed over the last 40 years. So that's one observation, different points in time. And then we can combine these two perspectives, multiple observations with multiple points in time. This will give us so-called panel data. Panel data has the advantage, statistically speaking, it's very robust data. You get very good results, but it's very hard to actually collect the data because the cross-sections all need to remain the same across all time periods. And of course, since you're combining two different perspectives here, the statistics or mathematics behind the respective analytical methods also are more sophisticated than in either of these two perspectives. Therefore, most of what this book is about cross-sectional data analysis, and only in the later parts are we talking a little bit about time series data, but only in a relatively brief context. That's the first point I want to cover here, different data types. Next part would be the difference between quantitative and qualitative data. Quantitative and qualitative data is an important distinction because it tells us which data we can directly process statistically, mathematically, and which we first have to process to make it, analytically analyzable. If we have qualitative data, this could be something like artworks. We can see this, we can evaluate this, but we can we have a lot of problems. Let's say it like this. We have a lot of problems mathematically analyzing artworks like this. We could make it analyzable. We could, for example, assign each pixel for this digitalized version of a painting a different color code and then analyze these color codes. But as I said, first off we have to digitalize the picture, the image, and then we have to assign the color codes, and then we have to write a program which analyzes the picture based on color codes. So there's a lot of preliminary work involved with analyzing qualitative data. Whereas on the other hand, if we have quantitative data, that's usually data already given as a number. That's very easily processed. If you have the income data of different people, if you have the GDP of different countries, you can very easily directly calculate average income, average GDP, GDP per capita, fluctuations with the variance, and something else. So quantitative data is much easier to be evaluated, to be analyzed, especially statistically, than qualitative data. That's the first part. The second or next part then would be so-called descriptiveness of data, or the difference between descriptive and non-descriptive variables. Descriptive means that, for example, there could be more than one existing value for a certain variable. So, for example, about owned cars. You can own one car, and then it states, for example, this guy owns Mercedes, this and that. But you could also own more than one car. Then it goes like Mercedes, BMW, Toyota. So owned cars is a so-called descriptive statistic because, well, you could have one value, you could have more than one value. Same goes for other things like how you consider, for example, first names. I myself have 2 first names, so it's also descriptive. Even though there are a lot of people with only one first name, but since it allows for multiple first names, it's descriptive in nature. Non-descriptive data only allows for a single value. So one example could be actual accepted pope. There's only one pope who's the active pope, and there's not a possibility to have like 6, 7 popes at the same time. Well, in history we had discussions with, well, there was one pope in Avignon, there was one pope in Rome or whatever, and there was usually afterwards decided that only one of them was the legally right version of the pope. So maybe not at the time, but in general we could say that's a non-descriptive office. There's usually only one in availability. So if you build for example, survey with descriptive and non-descriptive data. Here you have to give the test persons multiple answer opportunities, whereas here they only have to have one answer possibility because they can just fill in one single answer. Well, there might also be different other non-descriptive statistics. That's again, if I take first names I said, well, it could be multiple first names. But then again, even if I have 2 first names, like Jens Kai, they could be together considered as first name. So in this case, if you consider first names to be jointly used as the first name, even if they have different parts, then first names would be non-descriptive in nature as well. So here we also see how we think about certain variables, how we interpret them, might make a difference whether we're talking about descriptive or non-descriptive data. Well, that's about it on descriptiveness. Then we have the difference between continuous and discrete data. Continuous data is something where you can make the distance smaller and smaller and smaller, and it doesn't matter how small the distances become. For example, with time. We could say we measure this in years, or in days, or in hours, or in minutes, or in seconds, or in parts of seconds. So we can always make this smaller and smaller and smaller and detailed in each step. Whereas with discrete data, it's usually that there's no possibility to go somewhere in between. So if we talk about the number of books in a library, we could say it's like 860, and if I get one more book, it's 861. But I will never have 860.389572 books in a library. So that's discrete data because I cannot put, in a sensible way, values between integers. There's actually a lot of information which is stored as discrete data. Then again, there might be something which is in between those two, which we would call quasi-continuous. That's something like income. Because if you earn income, it's usually only on 2 digits after the decimal point. So if we talk about euros, it's in euros and cents. Same goes for the US dollar. It's usually in dollars and cents. Theoretically, you could make it much more detailed, but it's usually treated as discrete because you stop at the cents level. Since, however, you could theoretically make this smaller, we can process this as if it were continuous, and something like this is then called quasi-continuous. So it has all the properties of continuous data, even though if we take this strictly, it would be discrete data. Well, that's on continuous versus discrete data. The last part I want to talk about is about scale levels. We have 4 different scale levels we're going to differentiate between here. That's nominal, ordinal, interval, and ratio scaled. Nominal data, in this case, we can simply say how many of each object we have. For example, car brands. I can say, well, there in this parking lot are 2 Mercedes, 1 Fiat, 1 Audi, 1 BMW. But I cannot say, well, this brand is more of an automobile than that brand. I cannot say that Ford is more of a car than, for example, Toyota. I cannot order the car brands according to their, that's called as carness. And whenever I have something like this where I can count, but I cannot impose some kind of order, then I have nominal data. Same would go, for example, for job titles, for gender, something like this. So that's nominal data. That's the most restrictive type of statistical data. Then we have ordinal data. I have an order, for example, church or military hierarchies. I know who's the superior of whom, but I not necessarily know something about the distance. So I cannot say that, well, the distance between the Pope and a cardinal is twice the distance between a normal priest and, I don't know, a bishop. So that's a problem. I have an order, but I do not have a well understanding about the distance between 2 different outcomes. That's the different thing with interval data. I know the distance. That could be, for example, tone heights. I know the distance, but there's no absolute zero. Well, the absolute zero is best explained if I talk about year data. If I have yearly data, I can say, well, the year 2000 is actually 100 years after the year 1900. So I have distances. Mathematically speaking, I can do addition and subtraction. But what I cannot do is multiplication. I cannot say, well, he's born in this year, so therefore, if he's born in 2000, he's twice as old as someone who is born in, 4,000? 1,000? It doesn't really make sense. That's the same thing if we take temperature. If we have the Celsius scale, we cannot say, well, yesterday it was 0 degrees. Today it's twice as cold. Doesn't make sense. That's because there's no absolute zero. With tone heights, we can go up and down the tonal ladder. With temperatures in Celsius or Fahrenheit, we could go in minus areas and in plus areas. Same with the years. We could go AD, we could go BC. So there's no absolute zero which limits this to the lower the downwards region. That's what interval data is about. We can differentiate between distances. We can actually measure distances, but we cannot refer the distances to an absolute zero. That's different with ratios or with ratio scaled data. With ratio scaled data, we have something called an absolute zero. There's like an income of zero. You cannot have a negative income, at least not in a sensible way. That's why we can say, well, that guy earns 4,000 euros, therefore he earns twice as much as someone who earns 2,000 euros. We can do this with age as well. I have a guy who is 20, thereby he is half the age of someone who's 40, because it doesn't make sense to talk about someone who's minus 8 years old. That's the property of ratio data. Here we can use multiplication and division of the data as well. Well, that's the 4 general scale levels used in statistics. However, in many cases, we summarize them a little bit. We talk about nominal data, we talk about ordinal data, and then we summarize interval and ratio scaled into so-called metric data, or sometimes also called cardinal data. We're doing this because for some statistics, we just need them to be either interval or ratio scaled. So that's why it's called metric. So we just say, well, one type of statistic works for nominal, one type of statistic works for ordinal data, and one type only for metric data. Could be both of those. For example, the arithmetic mean, the average, only works for those two. So it only works for metric data. And well, that's then everything there is as introductory terms which I wanted to talk about. Hope you enjoyed this session. I say goodbye and see you next time.